Hello and welcome to Mr. Linford's math course. In today's discussion, we're going to be introducing ourselves to a new function type to be working with, and that is the logarithmic function. We're going to define what a logarithmic function is. We're going to compare it to our previous work with exponential functions. Then we're going to explore the graphs of logarithmic functions, try to pick up on some of the graphical features that they demonstrate. Then we're going to go over how to actually go ahead and numerically evaluate a logarithm, as well as answer some application questions. Let's first begin by defining what a logarithmic function is. So we're going to define a logarithmic function as a function, first and foremost, a function of the form, and I'll write it down here, f of x equaling log, that's the symbol, it's L-O-G, it's short for logarithm, and then I'm going to put a little subscript here, b, okay? The way this works, I'm going to write a little bigger. You have log, that's an operation, that's the name of an operation, and you have what's called the base value. It's like a subscript. Imagine like you're working in a chemistry class, H2O. That's a subscript. Same thing here. So this value called the base is a small subscript that we write. Then we're going to write in parentheses on the same kind of level as the logarithm, x. This right here is the parent function. This is the basic form of a logarithm function. We have log base b of x. So let me write that down. This would say log base b of x. That's how we would read this. Now, I should also put in here that b is in fact a real number, and we'll adjust this definition as we start to explore the graph, but this is generally what we have going on here. We have some logarithm where we have a specific numerical base value, and then we have an x component, or we have some expression in the parentheses here. I should define these components b as the base, and the x that's in the parentheses here, we're going to call that the argument. So whatever's on the inside of the parentheses is the argument, and that little subscript is the base. Now, the logarithm is in fact related to the exponential function, and here's how. Let's say that we are taking a logarithm. Let's say we have the logarithm, and I'm going to put the base in blue, some base, and let's put the argument as something like, let's say, x. I'll put that in red. This is going to equal, this logarithm will hopefully equal some number, we'll call it y. Okay? The exponential is the inverse of the logarithm. Logarithmic functions and exponential functions are in fact inverses of each other. So what I can say is, if this is the logarithmic expression, I can rewrite this to be an exponential expression. It would be b to the y power equals x. This is, on the left-hand side here, is the logarithmic, and on the right-hand side is the exponential. This is how the two functions are related. The purpose of the logarithm, I know it seems kind of odd right now, but logarithms were invented a long time ago to determine what exponentials were. What I mean by that is, let's say you knew some number b raised to some power would get you x. The question was, how do we find that exponent? Maybe it would be helpful if we plugged some numbers in here. I would have known very easily that 2 to some power would have given me a number like, oh gosh, let me think. Let's say 32. Okay? I'm just making up an easy example right now. I know that 2 to some power would have given me 32. But how would I have been able to determine what that exponent was? How would I know 2 to what power got me 32? I would need to find, because I'm trying to find this component of the function, I would need to have an inverse function. That's where the logarithm came. The logarithm said, if you're trying to find what exponent gets you this, all you need to do is take the log, the base number that you're working with is 2, and your argument, what you want to get 2 into, is 32. This will in fact equal the exponent that you are seeking. Sorry, I like color coding things. So this unknown exponent that you're trying to figure out, you can use the logarithm method to figure it out. That's what this is saying, okay? It is important, actually I would say it's almost vital for you to remember this connection. It's so incredibly important and necessary. If you're going to work with logarithms and exponentials, you need to know how they're related to each other. Use symbols, use number examples, whatever. It's very important for you to, 1, know how they're related to each other. And 2, I always say to students, when you're trying to remember how to structure a logarithm, use the vocab for 1, but also use your understanding of what the purpose of the logarithm is. Always remember that logarithms were really invented to tell you what the missing exponent was. We're going to keep this in mind in a little bit. We're going to actually go ahead and try to evaluate logarithmic expressions. By evaluating them, we're going to need to know how the expression would have worked in the exponential. So we're going to see this in just a little bit, but what I'd like to do right now is take a look at the graph of what's going on. I want to take a look at the different graphical features that we see when we go ahead and graph the parent function. So let's play around on Desmos a little bit. Let's see if we can get a picture of what's going on, and let's see if we can use that to help inform us about evaluating logarithms. So I'm going to go over to Desmos. We're going to start by taking a look at the Desmos graph, the logarithmic functions. You'll notice that I have the first spot filled in with the parent function, f of x equaling log base b of x. Hopefully you can see that that b is in subscript. It's a tiny small b written almost like the opposite of an exponent. Now, we want to see what happens for different values of b. So I have a slider here, and I'm going to click and drag and move this around and see what I get graphically as b changes, as the base changes. So I'm going to click on the slider and, hey, there's a graph. And then, oh gosh, there's another graph that I'm seeing. Take a look here. Notice that I just had 2 different graphs get produced. I started at 0, and at 0 I didn't see anything. But as soon as I started dragging it over, I have this kind of downward curving graph. Then it disappears at 1. And then slowly after 1, it reappears, but this time it looks flipped. It's now kind of curving up and to the right. What is going on here? Take a look. As I keep increasing, it keeps bending down more and more. As I decrease, it bends up more and more until it finally disappears, and it's almost flipped the other way. Okay, so I see that it disappears at 0, it disappears at 1, And negatives, it's also disappeared. I don't see a graph whenever b is negative. So what's going on here? I'm going to hit play on this slider, and it's just going to move around these different values so we can see what's happening for all the different values. We can see how the graph is bending and appearing and disappearing. What I'd like you to do is jot down what you notice about this graph, what you notice for these different b values. You see what happens when b is negative, when b is positive, when it's 0, when it's 1. We have the graph sometimes curving up and to the right. We sometimes have it curving down and to the right. What's going on here? Take a minute, jot down what you notice, and then we'll see where we're at. All right, well, hopefully you had some time to get down some of your ideas, but hopefully you're noticing that the graph that we have was always altering based on whatever b was. Based on whatever that base value was, we would have a different either shape to the graph or a different orientation entirely. Or maybe we didn't have a graph at all. So there were a couple weird cases. We had some situations where b was greater than 1. We also had weird situations where b was less than 1, but still in between 0 and 1. We also had the situation where b was less than 0, or even when it was equal to 0 or equal to 1. So what's going on here? Well, let's first take a look when b is greater than 1. When b is greater than 1, let's go ahead and I'm going to set it to something like 1.2, 1.5. Here it's at 2, and then at 3 and 4, etc. What do we see going on here? Well, as we set it to be greater than 1, we can tell that this graph is always curving up and to the right. So here I've said, let's go from b being 1 to 10. All these values greater than 1, you can see that it always has this unique shape of going up and to the right. So let's go ahead and jot that down. So for b greater than 1, we can say that the values for f of x, that's your output values. So the values for f of x, what you get out of the function, increase as x increases. And we can see that on the graph here, that we keep moving upwards and to the right. This graph is increasing. You can see it's slow to increase, but it's still increasing nonetheless. Very, very slowly, we're climbing up higher and higher in output values. So maybe let's write that down. The values of f of x increase as x increases, and in parentheses, I'm going to write that we are increasing very slowly. That's something that you see with this shape, this logarithmic shape to the graph. Instead of working with exponentials where we could increase very, very rapidly, logarithms increase very, very slowly. Now, that's what happens when b is greater than 1. Let's see what happens when b is between 0 and 1. So I'm going to alter the slider here. Let's say we're between 1 and 0, and let's start at 0. So let's go ahead and see what we get here. I'm going to hit play. And now what do you notice about the graph? It has a different shape, doesn't it? This time it's got like a decreasing shape. It's bending down and to the right. It looks like the closer I get to 0, the more L-shaped it is. Do you notice that? the closer I get to something like 0, it's almost looking like an L. It's bending up towards the axis. But notice that it still keeps decreasing. It still keeps shooting down more and more and more, right? It doesn't actually taper off. It keeps decreasing ever so slightly, but it still keeps decreasing. It keeps bending down. But as I get closer to 1, the curve opens more, and you'll notice that I keep opening downwards. So maybe we should make note of this. We can say that when b is between 0 and 1, the values of f of x decrease as x increases. And again, this does so very slowly. Let's take a look back at that graph. We can see that as x increases, our output values keep decreasing, but they do so rather slowly. I'm over here in like the 175 area, and we're only down by like 17 units. And I keep moving out, I keep moving out, I keep moving out. Finally, I'm down another about to 20, and I'm in the 300s. So we can see here, as exponents were able to grow rapidly, logarithms tend to decrease very slowly, or increase very slowly. Now we have the weird case, when b is less than or equal to 0. And maybe I should also throw in there, when b is equal to 0, well, I guess we already have that. When b is less than 0, when b is equal to 0, and when b is equal to 1. In these situations, there appeared to be no graph. And why was that? Why was it that there appeared to be no graph whenever b was negative, 0, or 1? Well, maybe let's try an example of something. I'm going to go and let's start with b equaling 0. I'm going to recreate a logarithm. Log base 0 of, well, let's say it's 2. Okay. Log base 0 of 2 equals some unknown. And in fact, I'll color that in red. Well, if I were to rewrite this as an exponential, I would say that my base number is 0. Remember, logarithms always would spit out an exponent. So this unknown is my exponent. That's what I'm trying to find. And it would equal 2. That's what this is saying. I have the base 0. It's going to spit out, and the logarithm spits out an exponent, so that's my exponent. And I'm trying to get 0 into 2 here. So let's try to think about this problem. 0 to what power gets me 2? Well, nothing. There's nothing that would work here. So this is not a possibility. Let's change it around. Let's say instead of 2, let's say I wanted 3. 0 to what power got me 3? Well, again, nothing. This doesn't work for any number. Really, the only number that this would work for would be 0. And I guess 0 to what power gets you 0? Well, any power. Well, keep in mind, 0 to the 0 power doesn't necessarily really equal 0. So this is a case where we have a bunch of errors getting produced. There is no way for us to take a base of 0 because I can't turn 0, raise it to a certain power, and turn it into any other number. So that's why we are not going to have b equals 0. We're going to say that you cannot choose 0 for a number. Okay, what about negatives? Why can't b be a negative? Well, let's try another example. Let's say the log of, all right, let's pick a negative number. Let's pick -2. Log of -2. And let's say that's got to equal something like 4. All right? What would that be? Well, -2 to some power getting me 4. Oh, I know what that power is. It's 2. Okay, that's actually fairly easy, right? I know that works. So log -2 of log base -2 of 4 should in fact get me a +2. Now let's take log of -2 for 8. -2 to what power gets me 8? Well, let's see. -2 times -2 times -2 is, oh, that's a -8. Oh, shoot. There really isn't a power that does that, is there? Because -2 to the third power is -8. So we have a problem here, don't we? This isn't going to work. Similar to what we saw with exponents, when you're dealing with logarithms that are negative values, you get sporadic, discrete graphs. You get graphs that might have a couple points spread around the graph, but you don't have something continuous, okay? What I mean by that is, let's take a look at Desmos. When b is a positive number, these graphs are continuous. There are no holes in the graphs, there are no skips, it's just one consistent line, okay? If I had b be a negative number, I wouldn't have just a solid curve or a solid line. I'd have a bunch of dots spread all around the graph. That's what the problem is here. So that's why we're going to say b can also not be a negative. So b can't be 0 because it's really impossible to take 0 and turn it into any other number by raising it to an exponent. And we also can't have negatives because a lot of times they give you contradictions. A lot of times there is no possible answer, and it's not a continuous graph. It's just a collection of random points. Or I should say it's a collection of just points. So now let's see what happens if b is 1. Let's take another example here. Log base 1 of, I don't know, 2. And we're going to say, what does that equal? Well, remember, we are asking ourselves, how do I take 1 and raise it to some power to, in fact, equal 2? Is that possible? Can 1 to any power get you the number 2? Well, no, because 1 to any power isn't 2, it's always 1. And that's true even if I change this argument around. Instead of 2, let's say 3. Can I raise 1 to any power to get 3? No, there's no way. The only time that this would work is if the argument was 1. Can 1 to what power gets you 1? And then you would just say, well, any number, right? Any number entirely would do that. So that's why we're also not going to have b equal 1. Because if you have it equal to 1, it's not going to work for any value you plug in for x, except 1, but that doesn't really tell us anything. So we have some restrictions we should probably put on the definition of a logarithm. So let's go back a little bit. I'm going to, in a different color here, put some restrictions on this definition. We're going to say that a logarithmic function is a function of the form log base b of x, where b is a real number. I'm going to put here and b is greater than 0 and b is not equal to 1. okay? You have to be greater than 0 for 1, and you can't equal 1. You can't have a base value of 1. So this, I would say, is our full official definition of a logarithm with our new restrictions added in. Now let's go ahead and let's actually go and define some specifics to the graph. So we have the parent function log base b of x. We have two different graphs we're seeing here. And that should make sense because exponentials had two different graphs as well. Two different shapes, I should say, to the graph. There was exponential growth and exponential decay. Well, similarly, we could have logarithmic growth and logarithmic decay. And what are those situations? If we're in the situation where we're between 0 and 1, we can see that as x increases, no matter what b is, let's say b is really, really small, like 0.12, our outputs keep decreasing, don't they? Our red line keeps getting lower and lower. Very slowly, but it does keep getting lower and lower. If we even increased b to be something like 0.86, we're still decreasing. Maybe a little bit faster, but we're still decreasing as x increases. As we get bigger and bigger x values, the outputs keep getting smaller and smaller. So this is the form of exponential decay. Exponential growth, let's reset this. I'm going to say from 1 to 10. And let's start at 1. Let me hit play on the slider. And we can see that as x increases, our graph increases as well. Our output values increase. So let's start with a number like 2.71. Okay, there's a specific base value. You can see that as x increases, our graph keeps increasing as well. Very slowly, but it does keep increasing. It does keep getting bigger and bigger. As I make the b larger, my graph, it bends down more and more. So let's say the b is 10. You can see that we're bent down quite a bit more. The curve is bent down closer to the x-axis, but it's still increasing. As x increases, the graph keeps increasing as well. Again, very slowly, but it's still increasing nonetheless. So we're going to go back and define these as logarithmic growth and logarithmic decay. So starting off with growth, we can say logarithmic growth is when f of x increases as x increases. And if we made a little graph here, we would see that it has this rather new shape to us. This kind of bending up and then kind of horizontally shape is going to be a new one that we're working with. So let's go ahead and say it kind of does this. So we can say as x increases, so does our output. This occurs when b is greater than 1. That's when we have growth. Now decay was the opposite. Decay occurs when f of x decreases as x increases. You might say they have indirect of a relationship. So let's get a little sketch of the graph here. This one, let me see if I can draw that a little better. This one will have a different shape, but again, something that we're going to have to get used to. This shape is one where it's almost like we inverted the graph. It comes down and curves out like this. So we can say as x increases, the output decreases. This occurred when b was between 0 and 1. When you had small decimals or small fractions that were b. So this is when we have the shape of growth and the shape of decay. Make sure you have these memorized, these shapes, you're understanding the shape of the graph, and make sure you know when they occur. Now let's talk about the domain and the range of the logarithm. Going back into Desmos, we can see that for the decay, and let's go ahead and let me change this up a little bit. Let's go from 0 to 5. Whether we're in decay or we're in growth, we have the same range. Let's start with growth. This red line is shooting down towards infinity. It keeps going downward and downward and downward, okay? While this side keeps increasing. It keeps going up and up and up. Very slowly, but it still keeps increasing. Now let's get into a decay situation. Here we have logarithmic decay. We can see that we're going up towards infinity, obviously. The red graph keeps increasing up and up and up towards infinity. But then as we come down here, it starts going down towards negative infinity as well, just very slowly. Notice that we keep decreasing in the graph. A lot of times people think with logarithms, they tend to think that the graphs are going to taper off and run perfectly horizontal. That's not the case. That doesn't happen. What you have here is you have a graph that slowly keeps decreasing. Or you have a graph that slowly keeps increasing. So we can say that the range for these is always negative infinity to positive infinity. So if we wrote this down, the range would be negative infinity towards infinity. No matter what shape you make the graph, whether it's curving up and to the right or down and to the right, it's still negative infinity to infinity. Now let's determine the domain of the graph. Taking a look back at Desmos, we can see what the set of all x values for the coordinate points are. Remember that when we look into the domain, we're looking to see how far left and how far right does the graph go. Well, as x increases, the graph keeps moving out towards the positive infinity direction. By this I mean, for all these different x values, you have coordinate points. So our graph keeps moving to the right towards positive infinity, but the left, it appears as though the graph curves upward. And this happens whether or not we're in decay or we're in logarithmic growth. In both cases, our graphs move out to the right towards positive infinity. However, the left-hand side of the graph always seems to have this curve that follows along the y-axis. Does it ever hit the y-axis? Well, let's take a look here, and we can see that, in fact, oh, no, it does not. It looks like we are getting incredibly close to the y-axis, but never actually hitting it. We can even say to ourselves, well, we know that's a fact because we know what would happen if we plugged in 0 for x. Let's take a look at that. Let's take a regular logarithmic function, log base, 2, and let's plug 0 in for the argument, 0 in for x. That's going to get some unknown quantity. So let's think, 2 to what power gets us 0? Does there exist an exponent that I could raise any number to get 0? Well, no, there doesn't. This is not a possibility. There's no way I could take 2 and raise it to any power to get 0. Some people might say, well, what about 2 to the 0 power? Remember, that's a 1. So this is why we cannot plug 0 in for x, and why graphically the line x equaling 0, or the y-axis, is an asymptote. That means that our graph is getting incredibly close to the y-axis, but never actually hitting it. Okay? That's a key fundamental idea. We're getting incredibly close, but we're never actually hitting it. So you can say that our domain, since we never seem to cross into the negative side of the graph, you can say our domain starts from 0 and goes off towards positive infinity. Now, since we never hit the line x equals 0, we're going to put a parenthesis there. We can get incredibly close to it, but we can't actually be at that line. So here's the domain and the range of the logarithmic parent function. This is the standard function's domain and range. Now let's take a look at some more key features. We already said that there is in fact an asymptote, and that's at x equaling 0. Okay? We have this x equaling 0, which is, by the way, the y-axis, as an asymptote because this is the value that produces a contradiction. So 0 being the highest value that produces a contradiction for us. And I should say here, this is the value that produces a contradiction. I should say when the argument is 0. That's when we get the contradiction, when this whole inside part here is a 0. Now, let's talk about some key points. I want to go back to the graph with the slider, and I want us to see, are there any points in particular that you notice continuously occurring on the graphs? Now back here in Desmos, what I want us to do is see if we notice any particular points occurring continuously on the graph. As we keep changing this graph, do you see any point that stays solid, that really all of these graphs share? Take a minute, take a look here. Well, hopefully you're noticing that in fact there is a point that they all show. And I do actually have it currently listed. It's the point 1, 0. I'm going to label that point. I'm going to have it pictured right here. Here's the point 1, 0. Notice that it does not move. Every logarithmic curve, whether it's exponential or logarithmic growth or logarithmic decay, always has this point 0, 1. And why is that? Well, keep in mind, when I take the logarithm of any base and I plug 1 in for the argument, and I say that equals 0. Why is this true? Well, b to the 0 power being 1, anything to the 0 power is 1. So keep that in mind. Anything to the 0 power is 1, so that's why the point 1, 0 is featured on all of the logarithmic functions here. So no matter what base was, I always had 1, 0. So we can list that as a key point for us, 1, 0. And then let's go back and let's take a look if we can find any other points that are specific to their graph, meaning they're specific to certain b values, but let's see if they help us determine how wide or how narrow the curve is, meaning how much of an L does the graph look like, or how high up does it curve. So let's take a look back here. Notice that as b decreases, as it gets closer to 1, we get a wider curve on the red graph. But as it gets farther from 1, we have a much more dramatic curve. It gets narrower and gets closer and closer to the x-axis. It keeps bending down more. Well, what I'm curious about is what happens when we have the x value being b. I wonder what happens, and let me write this down in the notes. I wonder what happens when I have a logarithm of base b where the argument itself is b. what would that produce? Well, b to what power gets me b? That's just a 1. So we should note that whenever I plug b in for x, whatever the base is, if you plug that in for x, you'll get a 1 out for the y. Let's take a look at that on the graph. You can see I'm going to click this point here, B1, and we'll have it labeled. This is where the x value is whatever b is. So this slider dictates what b is. Right now it's set to 5. Well, when I have b plugged in for x, log 5 of 5, I get 1 out. Let's change that. Let's set b to be a, 4. And you'll notice that we now have the purple dot is 4, 1. Let's set it to be 3. It's 3, 1. Let's set it to be 3.5. It's 3.5 again, okay? Anytime we have the b, we know that at that x value, you'll have the output being 1. So this can help you determine kind of how high up the graph curves or how low the graph curves. So for example, let's say we had log base 2.5. I know that when x is 2.5, right about here, when x is 2.5, we should be up at 1. That would be right up here. So let's take a look at that, and let's see what would happen. I'm going to change b to be 2.5. 2.5. And what do you know? It does in fact work. When x is 2.5, the output was a 1. So we can tell 2 points on any of these logarithmic curves right away. We know 1, 0 is on all of them. And we also know that this b1 is on all of them as well. Whatever b is, that x value will give you an output of 1. So here are 2 of the main key points that we are going to work with and use when determining the shape and I guess you could say the width or the height, I guess, of the curves. Now let's take a look at these 2 basic logarithmic functions. What I want us to do is determine which of these demonstrates growth and which of these demonstrates decay. We also want to identify the domain and range of each and any asymptotes that they might have, as well as what key points do they have as well. Key points that they both share and any key points that are unique to them. Let's take a minute, pause the video, go ahead and fill this out on your own, and when we come back, we'll take a look at what we have. All right, well, hopefully this wasn't too difficult of a challenge for you. I hope you noticed that right away this blue function, in fact, is the one that demonstrates exponential growth. Logarithmic growth. And you should note that because the b here is 2. It's greater than 1, so we're going to be increasing as x increases. Then you could also say for the function f of x in the red here that it's going to be an logarithmic decay. And that's because its base of 1/4 is between 0 and 1. If you're between 0 and 1, if you're any of those small decimals or fractions, you're going to demonstrate logarithmic decay. You're going to decrease as x increases. Now, both of them do have the same domain and the same range. The range was always the same because we always go stretch down from one infinity to the other infinity. So that really can't change. Now, the domain would be the same for all of them, because you can't plug 0 in for either of these. 2 to what power gets me 0? There's no such thing. And then 1/4 to some power gets me 0 as well. Again, no such thing. So that's why we say that x equaling 0 is the asymptote. That's the thing that they're going to approach, but they can never be at because it wouldn't work for them. And of course, the key point 1, 0. You can test that. Go ahead and plug 1 in. 2 to the 0 power gets you 1. Well, that's true. And 1/4 to the 0 power gets you 1. Hey, that's true as well. So that's why this key point of 1, 0 is common for both of them. Now, hopefully you're also able to find the unique key points for each one. The blue graph, if I were to take log base 2 of 2, what would I get? Well, 2 to what power equals 2? That's just a 1. So, if I plug in 2, I should get 1 out for the output. And then we can use the same logic for problem 2. Let's take 1/4 to some unknown power, getting me 1/4. Well, that unknown power is just 1. So, if you plug 1/4 in for x, you're going to get 1 out for y. And that is where we're able to now really kind of determine a little bit more accurately how high up the graph goes, or how, I should say, how highly curved the graph is. So these key points are helpful when determining the graph and helping to get a better picture of what's going on. And of course, we're able to better see whether we're working with growth or decay. Now what I'd like us to do is take some time to actually check these two graphs. Let's take a look at them and let's see in Desmos if they fit what we were describing. So for the blue one, we're hoping for exponential growth, or for logarithmic growth. Don't worry, I'll get that right eventually. And for the red one, we're hoping for logarithmic decay. And we're also hoping to see that these specific key points are featured on the graph. So let's take a look here. Let's take a look at the first graph, the blue one. That was log base 2 of x. So you'll notice that we are in fact in logarithmic growth. We do have the point 1, 0 featured on the graph. It's on the blue graph here. Now what I want to do is I want to see if the point 2, 1 is on the graph. So I have to adjust the slider here to be 2. And if I can get it there, oh gosh, I'll just type it in. When b is 2, hey, we do in fact get that point 2, 1 is on the graph. So it does work out. Now let's take a look at the red function. Let's take a look at base 1/4 of x. You can see we are in logarithmic decay. It does have that point 1, 0, so we have the correct the correct x-intercept. Now let's set b to be 1/4. So I'm going to change this to be 1/4 or 0.25. And what do you know? It is in fact on the graph. You can see it right there. So our predictions were accurate. We were able to correctly establish that one would be the growth, one would be the decay, and we were able to find some points that they would have. What I'd like us to do now is take a look at what happens as we further manipulate the logarithmic function. So far, all that we've done is we've looked at the parent function of the logarithm, and all we've done is manipulated b. We keep changing the values of b, which is okay. But what happens if we start manipulating the function a little more? Meaning, what would happen if instead of having the argument of just x, what if we put in an expression for the argument? And what would happen if I took the whole logarithmic function and I added a value to it, or I subtracted a value to it? What I want us to do is take a look at Desmos and play around with some sliders on there. I have a new graph featured for this section of the notes. I have it linked down in the description. Both graphs that we've been working with in Desmos will be linked in the description, and they're going to be linked on the course website. So take a look at them, play around with the sliders. The one we're going to work with now is called logarithmic transformations. We want to see what happens when we do things like we manipulate the argument, or when we add or subtract quantities to the entire function. So let's take a look at Desmos. Let's take a look at this particular graph. You'll notice that I have the standard form of the logarithmic function that we're going to be working with here graphed in purple. It is log base b, and I've set b to be 2. We could change b around. We could say, I don't know, let's say it could be anywhere between 0 and 5, like we did before. And we could change b, and we could manipulate it. We could be anywhere in logarithmic growth, or we could be in logarithmic decay. But let's just take an example. Let's say b is going to be 2. Just something simple to work with. So we have this graph. Also, notice that it's a little somewhat hard to see, but can you see this dashed line on the y-axis? That's x equals 0. So there's our asymptote, so we're able to have that on the graph. And you also notice that we have the point 1, 0, so there's the x-intercept that we expect to have. And we have the point 2, 1. So for that given b value, we have the output of 1. So this is standard, things that we've been working with before. What I want us to do now is I want us to start messing around with the function. We can start by, let's change the argument around. Before we had the argument was just x. Now, let's say I'm adding or subtracting values from x. By that I mean, let's go ahead and let's have numbers filled in for h. Right now h is set to 0. Let's set it to maybe a 1. What do you notice just happened here? Take a look. As I set h to be 1, I now had the function x minus 1. What happened? Well, I moved the entire graph over to the right. What happens if I have negative 1? Hey, it looks like I moved the graph over to the left. So this is not a new concept to us. In fact, let me hit play on this slider here. As we have done in the past, the same when we were working with quadratics and vertex formula, if you were to add or subtract values to x in the argument, you would shift the graph left or right. If you plug positive values in for h, so you have x minus 2 or x minus 5, you move things to the right. If you plug in negatives, like here I have negative 5.15, that would be x plus 5.15. That moves everything to the left. So take a look and see how we're moving around. All that this h does is it controls the horizontal shift. All right, let's set it back to 0. So we have just our standard parent function. Now let's look at k. What happens when we manipulate k? Well, whenever I add values to the function, I'm sliding the function upwards. And whenever I subtract values from the function, I'm sliding it downwards. You can see that when you add values, so when k is positive, you're increasing, and when it's negative, you're decreasing. You're sliding the graph down. That's literally what this is doing. It's called a transformation or a vertical shift. You're shifting the graph up with positive k values, and you're shifting it down with negative k values. That's how we're manipulating these functions here. Hopefully you're seeing that. What I'd like us to do for the time being is practice a little bit of this so we are able to determine where in fact this graph might be moved to. So let's go back into our notes and take a look at some examples. Let's first define the idea of vertical shift. The vertical shift is how far up or down the graph was moved. And we can say here what controlled the vertical shift was the k. So we can say we shifted up k units or down negative k units. So if k is positive, we're going up, and if it's negative, we're going down. Now, the horizontal shift is how far left and right we went. So let's say how far left or right that's a terrible the graph was moved. And by that I mean, how much did we slide it over? Now, if h was positive, we moved it to the right. So for h positive, we move it to the right. For negative h, we moved it to the left. So what I want to make sure we notice by this is we're subtracting h here. So if I had x minus some positive h, that moved the graph h units to the right. Let me get some extra space. If h was negative, if I was subtracting a negative value, that moved the graph h units to the left. Now it's important to note here, when I have the double negatives, you would see this represented as x plus h, okay? So if I had x plus a number, I have to move the graph to the left. If I have x minus a number, I have to move it to the right. Hopefully you're seeing how the positive h or the negative h impacts where it's placed. The last thing I wanted to talk about was domain, but let's hold off on that for just a minute. I want to not overwhelm us with too much information, but I'd like us to try to practice interpreting some graphs based on their shifts first. Here are some practice problems. I want us to start with problems 1 and problem 3. What we should do here is identify how we have moved the graphs. So in problem 1, has there been a vertical shift? Has there been a horizontal shift? So, has there been a vertical shift in this function? You should say no, there has not been, because there's no k value we've added to this. Additionally, has there been a horizontal shift? Yes, we've subtracted 5 from x, so that means we should be 5 units to the right. That's what we're anticipating here. Now let's take a look at the green graph. Has there been a vertical shift? Well, again, no, there should not have been, because there's no k value here. So we don't expect it to have moved up or down at all, but has there been a horizontal shift? And we expect there to, in fact, be at 1, because we're manipulating the x. The argument is now x plus 3. By the way, that's the same as x minus negative 3. So my hypothesis is that we moved 3 units to the left. I'm guessing that we are now starting in the negative portion of the x-axis. So why don't we go ahead and take a look at those two graphs. So here in Desmos, I'm going to unclick the purple graph, and let's take a look at the two examples. We had this one, the blue function, log of x minus 5, and we had the green one, log x plus 3. Let's start with the blue. You'll notice, hey, wait a minute. And in fact, let me get these coordinate points turned off here. You'll notice that here, our graph is no longer getting close to the y-axis. In fact, we've moved it over. Instead of being, approaching x being 0, now we're shifted over 5 units. And in fact, I bet this point right here is, let's see here, a 6, 0. And in fact, it is. So this graph was moved over 5 units to the right. Now let's take a look at the green graph. We suggested it be moved 3 units to the left. And what do you know it is? Over here, let's zoom in. Look at it. Instead of approaching 0, it's approaching -3. And we have the coordinate point -2, 1. I'm sorry, -2, 0. So this was in fact slid over 3 units to the left. So our anticipation of the shifts, of the vertical and horizontal shifts, was correct. Now what I want us to do is to try to determine the domains of these particular functions. What do you notice about the blue graph here? What do you notice about its domain? Well, it's no longer approaching the y-axis. Instead, it's approaching the line, instead of being x equaling 0, it's approaching the line x equals 5. We're getting incredibly close to that line. And in fact, it looks like we're about there, but it turns out we're just incredibly close to it. So we're approaching it. So our asymptote has actually moved. Let's take a look at how that asymptote has moved. Here, h was a 5. So let me set h to be 5. And you can see, wait a minute, take a look here. That is, in fact, the asymptote. So how does this affect our domain? How does log x minus 5 affect our domain? Well, one thing that you should notice is that in the previous situation, when I had a logarithm with x as the argument. Oh, and by the way, I'm just now noticing I haven't been writing a base down here. If I don't write a base down there, if it's not written, it's implied that I mean base 10. Okay? That's usually what is done with the calculator and what the book does. Log, and if nothing's written there, if I just write the argument, you can expect there's like an imaginary 10 down there. So, for all of these, the base is a 10. We just don't always write that. That's what your calculator is programmed with, by the way. So when you use the log button on your calculator, the base is automatically set to be 10. So you'll oftentimes notice it's not listed as the base. It's just because what it's set to automatically. So anytime I don't write it down there, just assume it's a 10. Where was I? So in this situation, we said that the domain had to have positive x values. We said the domain was 0 to infinity. Well, that was because we couldn't have the argument x be 0. X here had to be, the argument had to be greater than 0. Well, in the example we just saw, we had the log, base 10, of x minus 5. In this case, again, we want the argument to be greater than 0. That means x has to be greater than 5. What would happen if I plugged 5 in for x? Let's take a look here. If I were to plug 5 in for x, I would get log base 10 of 0. And we can't have the argument be 0, because 10 to what power gets you 0? Nothing. It doesn't work. So, what we're going to say here, whenever we perform a vertical shift, we change the domain. So, when determining the new domain, because anytime you perform a vertical shift, the domain becomes new, all right? Because you've slid over the graph. You've slid over kind of where it started. So we're going to say the domain should be determined by the values that keep the argument greater than 0. So the domain is what values can you plug in for x to keep the argument greater than 0. So let's take a look at that in this problem. We said x minus 5 has to be greater than 0, so x has to be greater than 5. So our domain, I'll just write that as a D, the domain should be 5 to infinity. And we can see that on the graph. Take a look here. We are, like we said, approaching the axis, or we are approaching, not the axis, the asymptote. And we are getting incredibly close to it, but we're never actually hitting that line. So this is the starting point for the graph, 5. And we then go out towards infinity. Now let's see if we can determine that for the green function, the log of x plus 3. Well, you should notice here that the argument is x plus 3. That means that we want to pick x values that keep x plus 3 greater than 0. So x plus 3 must be greater than 0, so x must be greater than negative 3. Don't plug in negative 3 or anything smaller than it. Our domain would go from negative 3 to infinity. If you plug in negative 2, you're good. If you plug in negative 1, you're good. Plug in 0 for x. Plug in 10, 20, whatever. Just don't plug in negative 3 or anything less than that. So let's see that on the graph here. Here's the green function, and h was said to be a negative 3, so let's make that negative 3. And you can see, yes, that is in fact the asymptote. Negative 3 is the asymptote. We're getting incredibly close to it, but we never actually hit it. So we can plug in any of these x values, and we would get coordinate points for them. Just don't plug in negative 3 or anything less than it. So this is how we're affecting the domain. We're just sliding it around on the x-axis. Hopefully this is making sense to you. Hopefully you're getting a picture of what's going on. Something I really want to take a minute to highlight. Before we said you can't plug 0 in for x. What I was trying to be careful to say was you can't have 0 be the argument. So that's what gave us the issue here with the previous domain. We couldn't have 0 for the whole argument. That's what I was hinting at before. Now that we're getting into the situation where we can change the argument, where we can add or subtract values to it, we're saying, again, you could plug 0 in for x. You just can't have the argument be 0. So that's a key idea here. The argument has to be greater than 0, not necessarily x, okay? So don't be shy to the fact that when you look at an example like this, hey, I could plug 0 in for x here. I would get log of 3. That's totally allowed. That's fine. I can't plug values in that make the whole thing 0. That's what we're trying to get at. What I'd like you to do right now is I want you to take a look at these two functions here, the red and the orange function. What I want you to do is I want you to try to determine what the horizontal shifts have been on them and try to determine what the domains might be. Take a minute, pause the video, and let's see what you come up with. Something you should notice about this particular function, we're going to start with the red one, is that we now have a number out front of x. What we can do here is factor the 4 out. We could rewrite this as, here I'll do this to the side, log 4 of x minus 5. We just factored out a GCF of 4. I'm going to suspect here that our horizontal shift is going to be 5 units to the right. I'm suspecting it because the things that control the horizontal shift are what is being subtracted from x. Sometimes students would say, 20. We have moved the graph 20 units to the right. But keep in mind, this negative 20, you're subtracting 20 here from 4x, not 1x. Here, I'm subtracting 5 from 1x. That's why I'm going to say we're moving 5 units over. If you want to determine the horizontal shift, you have to have the leading coefficient be a 1. So, what's a quick way of doing that? Just factor out the leading coefficient. Easy as that. So, we should be 5 units over. And let's take a look at that graph. We're here in Desmos. Let's take a look at this red graph right here. We are, in fact, 5 units over. H here is 5. Let's see if I can set it there. So we've moved 5 units over to the right. So this shouldn't be anything new than the original blue function we worked with. So let's talk about its domain. We know that we have shifted it over 5 units, and we know that the argument here, the 4x minus 20, has to be greater than 0. Well, that just means 4x has to be greater than 20, and x must be greater than 5. So, again, we can see that the domain is going to be 5 to infinity. So it seems like these two graphs might be the same thing. We have no vertical shift. All we've done is shifted it horizontally 5 units, and it has the same domain. But the arguments look different. Are they in fact the same graph? Well, let's take a look. You can see that I have graphed both the blue function and the red function. They have the same domain, 5 to infinity, and they were both shifted over 5 units. But the trouble is here, the red graph is a bit higher than the blue graph. The blue graph curves a little quicker than the red graph. It's not been shifted up at all, it's just bent a little differently. The reason for that is because I've multiplied these inner values by 4. What I can do here is I can change around this standard function that we were working with. I can take another value, let's call it an a, and multiply it to everything. And I'm going to add a slider for a here. Let me go back to the original function we were working with. Let's get back to the home screen. We'll set h to be 0, k to be 0, b we'll keep it as 2, and a is 1. Okay, here was the original graph that we were working with. Let's now change the a value. Let's change what I multiply to x. Notice what's happening here. As I change what I'm multiplying to x, The bigger it is, the higher the graph opens upward, the higher it's curving. The graph is curving, by the way. It's not sliding vertically. This causes things to slide vertically, the k. Here, the a is what's causing it to curve upwards more or downwards more. So as I open it up, it's curving more upwards. As I decrease it, it's curving downwards less and less, or more and more. And then when I make it negative, watch what happens. When we make it negative, it flips to the other side. If I multiplied all of these logarithm values by negatives, it would turn them negative. So hopefully you're seeing what's going on here. This is what happens when I'm multiplying by a specific quantity. That's why these two functions, their domains were the same, their asymptotes were the same, they were shifted over the same amount, but they still weren't the same graph because one was being bent up a little more than the other. Okay? I'm not going to be too picky working with this, so I'm going to go ahead and take that A out. I'm not going to be too picky with us working with that or trying to visualize what's going on. Just keep in mind, if the A is a larger number, it's bending upwards more, and if it's a smaller number, it's tending to bend downwards more. So let's go back to our practice here. And the last problem we have is the orange function. What I'd like us to do, now that we have reviewed the red function, I want you to pause the video, and I want you to try to see if you can identify what the what the horizontal shift has been for this, and if you can identify what the domain is for the function. All right, well, hopefully you reviewed the same process that we did before. To determine the horizontal shift, I need to know what was added or subtracted to x. Here, I know that I added 3, but I added it to 2x. I want to know what happened to just x. So what I did was I factored out a 2 from everything. And when I factored a 2 out, I was left with 3 halves. And that's okay. That's fine. Your logarithm functions don't have to be shifted over whole number amounts. They can be shifted over fractional amounts. That's totally fine. So the horizontal shift here is 3.5 units to the left. We moved it to the left because it's a positive value, right? This is the same as we're taking x minus negative 3 halves. Now let's determine the domain of it. 2x plus 3 better be greater than 0. Well, that just means 2x better be greater than negative 3. So x better be greater than negative 3 halves. So our domain here is going to be negative 3 halves. Let me try to write that a little nicer. Negative 3 halves to infinity. I've written both in parentheses here. And hopefully you're getting the hang of this and realizing that it's whatever we need to do to keep the argument from being 0. So again, this is just another type of function that we're adding to the functions that we've already worked with. Let's go ahead and check its graph in Desmos. You can see here that I've plotted the orange function, log of 2x plus 3. And it has, in fact, been shifted over to the left. It's been shifted over 3.5 units. That's 1.5 units. And I've gone and made the h 1.5. So we have our asymptote here at negative 1.5. So we can see that we're going from negative 3 halves, or negative 1.5, and we're going off to positive infinity. So we're able to determine the domain yet again from this particular function. What I now want to do is take some time to actually go about and learn how to evaluate logarithmic functions. It's a pretty easy task, but I think it's going to be important for us to make sure that we know how to do this, because if we understand what a logarithm is and we're able to get a good picture of it, we should probably be able to numerically work with them as well. All right, let's take a look at what's going on here. Remember, we are taking the logarithm. We're going to say it has some base, and we're taking it of some argument. And the logarithm will spit out a number. That number is the exponent. So it probably would be helpful for me to label these. That's the exponent. That is the argument. And here we have the base. We remember that this is, in fact, related to the exponential form b to the y power, getting us the argument x. This is how they're related. So what we're going to do for the first way of evaluating a logarithm, because there's a couple different techniques. We're only going to cover one right now. That form is basically going to say, convert your logarithmic expression into an exponential. So I'm going to say first, let's identify the base and the argument. Identify what the base and what the argument is. Then identify, or actually I should say, then label I guess I want to say label what the log equals. Meaning, set the logarithm equal to something. We'll see an example of this in just a minute. So identify the base and the argument, and then label what this whole logarithmic expression is equal to. Okay? Let's take a look at an example right here. We have something like log 16 of 4. The base, b, is 16. The argument is 4. And I should say that this is going to equal, I don't know, let's come up with a label. I don't know what this equals, so let's say something like y. I'm just making something up. So, now that we have it all labeled, what we should do is rewrite the log equation into an exponential equation. So we're going to turn the logarithmic expression into an exponential. So let's do that right here. We have this logarithmic expression. Let's rewrite it as an exponential. The base is 16. The exponent is y. And what this equals is a 4. Remember, the base is still the base number for the exponent. Logarithms always spit out exponents, so that's what my exponent is here. And it's going to equal the argument 4. Now that I've rewritten it, it should be fairly obvious for me, knowing my past work with exponents, to figure out what this is going to be. 16 to some power gets me 4. Well, what is that power? What would get me a 4? Well, hopefully you're saying 16 to the half power gets me 4. Because remember, anything to the half power is the same as the square root. So, y here should equal a half. What is log base 16 of 4? It's just a half. If I wanted to turn 16 into 4, what do I have to raise 16 to? The half power. So we can put that as our final step. besides rewriting the logarithmic equation into an exponential equation, we're going to want to use our knowledge of exponents to solve for the exponent. So let's try the next few problems. Here I have log 8 of 2, and that's equaling something. So I have 8 to some power gets me 2. Well, 8 to what power would get me 2? Well, 8 to the 1/3 power. If I took the third root of 8, or I should say the cube root of 8, I would get 2. So log base 8 of 2 is 1/3. How do I get 8 into 2 by raising it to an exponent? Well, raise it to the 1/3 power. Now let's take a look at this example. The base is 9, and I need to raise it to some unknown exponent to get the argument of 9/3. Oh gee, I wonder what I need to raise the exponent as. Well, hopefully you're saying 9 to what power is 9 to the 3rd power? That's just 9 to the 3rd. So we'll get a 3 here. Now, this is what we've already done before when trying to figure out and understand exponents. We use this to help us plot some points, so this really shouldn't be anything new to us. Hopefully, this idea is making sense to you and you're feeling a bit more confident with it. You're able to understand how to go about and evaluate logarithmic expressions. And then hopefully you're really feeling confident understanding their graphs and being able to determine how far they were slid over left to right or up and down and how that might have affected their domains. Now, I did have a application problem for us to practice, but I'm thinking, you know what, this video is getting long enough, might as well hold off on that. So we'll cover applications of logarithmic problems later. What I really want you to do right now is just make sure you're confident understanding what a logarithmic function is, knowing how it's related to the exponential, and making sure you can determine its domain and be able to evaluate them. If you have any questions or comments, please let me know. My email is klinford, that's KLINFORD, @wccnet.edu. And until next time, take care.